Hello class, this is part 2 of our lectures on strain gauges. So like it says here, strain gauges and low displacement cells. The low displacement cells is what we are going to be spending most of our time on today. There we go. So there you go, low displacement cells. There's a lot of info on this slide. Let's start up here. So we have a cantilevered beam, we have a base on one end, and then the load on the other end. And at some distance A out, we have 4 strain gauges. So in this view, you see them here. Then in this view, you see that there are 2 on the top and 2 on the bottom. And then the distance from those to the load is B. Now, there are a few other important things. The thickness of this and the width of this are important. And then the fact that the load is going to be bending the end down. So the 2 on top are going to be in tension, and the 2 on the underside are going to be in compression. And then we have these arranged in a Wheatstone bridge as shown here. So the 2 in tension, the 2 in compression, we have our input voltage and our output voltage. Like we learned in the last lecture, this would be a full bridge because we have 4 active gauges on here. The temperature effects will cancel out. That was part of the beauty of arranging them in this way. And that equation, so long as our 4 strain gauges are the same, as in they have the same nominal resistance, then we can use that equation for the full bridge. And I'm going to get to that eventually. So this just talks about all those dimensions and the load that I already mentioned. Now to start this out, as a review from mechanics of materials for cantilever beams, the axial strain is going to be equal to the moment times the C for the neutral axis, and then over the modulus of elasticity and the moment of inertia. So we're interested in what's happening here at strain gauges. So the moment is going to be the load times B. The neutral axis with a symmetrical crossbeam like this is just going to be the thickness, the dimension in this direction divided by 2. The moment of inertia for a rectangular beam is the width times the thickness cubed divided by 12. So we're going to substitute the M, C, and I into this equation. So we do that here, and then we can simplify it down to this. We're going to take this on the next slide. We have this up here. And the next thing that we need to do is to incorporate that equation for the full bridge, for 4 active gauges that are balanced to begin with. They all have the same nominal resistance. This is that equation. So the output voltage is going to be the input voltage times the gauge factor times the strain, axial strain. And what we're going to want to do is rearrange this for the axial strain. So we'll relate it to this up here. We have this in terms of the axial strain. We're rearranging this to be in terms of the axial strain. And then we'll just make this equal to this because they are. And we will rearrange for the output voltage. So we get this equation here. Now, this is going to be the output for a given load based on the various dimensions and material that's used and the gauge factor of the strain gauges. And the input voltage, if I didn't say that. So that in itself is something we would be interested in. And then something else that we're going to be interested in is the sensitivity of this load cell. And if you remember, there are often two sensitivities that we are interested in. One is just that change in output over the change in input. If we were in class, I would probably ask you for that. But the change in the output is going to be the change in the output voltage, and the input is the load, so it's the change in the output over the change in the load. So we just take the derivative of this with respect to the load, and we get this. So if we're interested in the sensitivity of this strain gauge load cell with the input voltage that we have applied to it, this is what we would use. But if we were interested in that the sensitivity of this independent of the input voltage, so somebody, you might be comparing this to somebody else's load cell and they're using a different input voltage. If you'd want to make that comparison, that is S2. So you just take that same thing and you take the input voltage out of it. So this. In lab, this is very similar to what we would be doing. What the lab does is there's a load cell like this. There are strain gauges on the top, on the bottom. There's also one on the base. So we can do all kinds of different configurations. We can do the full bridge like we discussed here. We could do two, so one active on the top, one active on the bottom. That would be a half bridge. We would just use fixed resistors equal to the nominal resistance of those strain gauges, in that case, for the other two resistors. We could do a quarter bridge, and we could do it with the dummy gauge that's on the base to cancel out the temperature effects. So we have that load cell apparatus, and we apply loads on the end. And what we would do is we would take this load cell, we would set it up in one of the ways that I just described, and we would connect this, we'd write a simple VI lab view so that we collect that output voltage. And for the loads, what the big idea is that we test the load ratings of fishing line, of tippet, fly fishing tippet. So for all the 7x, 6x, all these different sizes, there's a force rating for them. And we would be testing, we'd tie that tippet to the end of this, and we'd pull on it until it broke. And we would test to see that we're getting close to the ratings. For that to work, we would have to go through a calibration process. So that would be the first phase of the lab. We would set known weights on the end of this. We would measure the output voltage for those different weights. And then through that, we can get a sensitivity. And we would apply that sensitivity, apply a zero offset. So we zero out our strain gauge and we apply sensitivity. So our output is not in volts or millivolts, but it's in pounds force, or typically pounds force, because here in America, the tippet is rated in pounds. Part of what we would do in that lab is we would measure the sensitivity experimentally, like we just described, but we would also want to determine it theoretically down here. So you would be measuring the width and the thickness of the cross-section of that beam. You'd be measuring the distance from the base to the strain gauges, and then from the strain gauges out to the load. And you'd be told the material from all of that. You'd be told the strain gauge factor. So you would be able to theoretically calculate the load. And one of the things you'd have to do is compare those. So I think I said you'd be able to theoretically calculate the load. I meant you'd be able to theoretically calculate the sensitivity. And we'd want to compare your theoretical derivation of that and then what you get experimentally. That is the strain gauge load cell. Now, we have a true or false review question for you here about it. So it says, using a stiffer, i.e., or that is a higher Young's modulus beam, will increase the sensitivity of the full bridge strain gauge load cell. So think about that for a minute. I'll just shut up and let you think about it. What I was going to say was that it would be beneficial for you to have that equation. Normally, if we weren't doing this online, I would be writing out all those equations for getting to the sensitivity. And you would have it there in your notes. Or even if you're going through the slides, I'd probably give you time to write down that equation. You could look at that. I guess here you can pause it. You can go back, you can look at that equation and probably answer it by looking at that. But another way, you might just think about what does a stiffer beam mean in terms of when you apply a load to it, how is that going to affect the change in the output for a given load? So why don't you do that? Either pause it and think about it for a little while, or pause it and go back and look at that equation and come up with an answer. Since you can pause it and you can travel through time, we'll just go ahead to the answer. Answer is false. So if we look at those sensitivity equations, if it's stiffer, means Young's modulus is going to be greater, then since that is in the denominator, it means our sensitivity is going to be smaller. That would make it false. And then also what I was saying, where you might just want to think about what does a higher Young's modulus beam mean for sensitivity. If it's a higher Young's modulus, it's going to be stiffer, like the problem statement says. So you apply a load on the end, it's going to deflect less. It's going to bend less. So you're going to see less strain where the strain gauges are. So you're going to have, and that's going to relate to a smaller output voltage. So you're going to have a lower sensitivity. You could get there even without the equation. Moving on now, slightly different version of this is the displacement transducer. The main difference here is that instead of getting the output in terms of, or relative to the load that's applied, we're getting the output for a certain displacement. So most of this is the same. We still have the same arrangement of these in the Wheatstone bridge. The two on top are in tension, the two on the bottom are in compression. Really the only difference here is that instead of a load, we have delta for a displacement. We need to recall a few things again. So for cantilevered beam, rectangular cross-section, the displacement is the load times the length. So length is A plus B in this case. That length cubed over 3 modulus moment of inertia. So the second step here, we're just substituting in the a plus b for L. But here we are rearranging it for the load. And we're going to relate this to an equation that we came to in the load cell. So from that load cell, our strain was equal to 6 times the load times this dimension b over the width times the thickness squared over the modulus of elasticity. If we rearrange this for the load, we get this. And since P is equal to P, then this is equal to this. That's what we have here. And then we want to take that equation for the full bridge, the output voltage. So this is for the full bridge. It's balanced to begin with. The nominal resistances of all the strain gauges are the same. So we take this equation and we rearrange it for the strain, and then we substitute that in for the strain here. If we make that substitution and we rearrange it for the output voltage, we would get to this. So we're going to do a little bit more with this, but while I'm here, before I forget, I mentioned that in the lab, I'm not exactly sure what we're going to have you do in the lab yet. There are a number of different variations we could have done, like I said previously a few minutes ago. Could be quarter bridge, could be half bridge, could be full bridge. Just note these equations here are for full bridge. If we needed to have you do a half bridge, for example, then you would want to substitute in a different equation here for your theoretical derivation of the sensitivity to compare to your experimental. So remember, the half bridge has a 2 in the denominator and a quarter bridge has a 4 in the denominator. But let's get back to this equation here. So we're going to move that up here to the next page. Then we need the moment of inertia for a rectangular cross-section. I think we already gave you that back for the load cell. We substitute that in for this, so we get this, and then we can simplify it down quite a bit to this. So this is our equation for the output voltage based on the displacement, all the dimensions, the input voltage, the gauge factor, all of that. And then again, to get the sensitivity, that S1 is going to depend on the input voltage. It's just the change in the output over the change in the input, which is displacement this time. So we take the derivative of this with respect to the displacement, we get this. And then if we want the S2, which is independent of the source voltage, we just take that VI out and we get this. So there are our 2 theoretical sensitivities for the displacement transducer. Now this is what normally we would be doing in lab. Unfortunately, you won't get to do this, but what we do, note we have this load cell here. And you need to, well, what you would need to do would be to take the rat and you have to insert its nose into the nose cone holder. And then you would take, excuse me, an electrode and you'd attach it to the right buttock. So this is usually the point where I can't go on anymore. The class is, half the class is looking at me with a blank stare, and the other half of the class is starting to laugh. Hopefully you got a little bit of a laugh in your coronavirus quarantine there. This isn't what we actually do in lab. So no 361 student has done this yet, but this is something that was done. There's a lot of biomechanics. There's a lot of study of animals to see how their bodies work, and then we use that in designs. So this is part of that. They're trying to measure the torque output of a rat ankle. They would use that electrode to stimulate it to get it to move that little foot pedal. Then through a sprocket, that ended up moving over here. We have this kind of like a cantilevered beam. There's some strain gauges on there. This was the data that was collected. So they got the torque under normal, fatigued, and then abnormal fatigued. Now you're probably really happy you didn't have to do this. Well, maybe some of you aren't. Maybe some of you would like this. I don't know. Sickos. I'm just kidding. Sorry. Going crazy here in quarantine. Anyways, we have another question. What electrical property changes when a strain gauge is strained? You have 4 choices here. I won't wait too long because you can pause it. Hopefully you get the right answer. D, resistance is what changes. The output voltage to the Wheatstone bridge changes, but when the strain gauge is strained, the change there is resistance. We have to apply a current through it to get the voltage. Now, we've primarily just been talking about axial strain so far. We mentioned transverse strain in the intro, just in the strain review. We're going to talk a little bit more about measuring it with a gauge now. So like this starts out, it says, often the structure surface is stressed in more than one direction simultaneously. Biaxial stress. So we have axial strain and transverse strain at the same time. Manufacturers of strain gauges consider this and provide a transverse gauge factor. So we have that here, similar to axial in form, just different. It's for transverse. And then we also have a transverse sensitivity. However, that KT, that transverse sensitivity, is usually very small and neglected. So we need to measure multi-direction strain in a different way then. How do we do that? We do that with a strain gauge rosette. This is what one looks like. This is blown up. I guess maybe you're watching this on your phone and maybe that is about right size, but on my screen, this is blown up larger than it actually is. But the main thing is you have these strain gauges in these 3 directions. So we have this direction, and this direction. The main point is that to determine the strain in any direction, so any angle from X, we can determine the strain based on this equation. Now, some of this isn't quite as straightforward as many students initially think. The first part of it is, so the strain in this direction is just going to be equal to the strain from this strain gauge. The strain in this direction is just going to be equal to the strain from this gauge. That's straightforward. But and those 2 things are used in this equation up here with the angle that you're interested in. But this component, the shear strain, that is not this gauge. So shear strain is not just the strain in the 45-degree angle. We do use that we actually use all 3. So use the 45-degree, the 0, and the 90-degree in this equation to get the shear strain. And then that shear strain is what we use up here to determine the strain in any particular direction. So this one is the rectangular strain gauge rosette. Oh, I think we're going to get to another type, but first I want to show a little bit more about that shear strain. This probably should just be a review, but maybe you forgot. So like we said, the shear strain is not the strain along the 45. So this figure down here will help. So it says to define shear strains, it is necessary to look at two directions that form the plane that undergoes shear distortion. So we're looking at the strain in two different directions to determine that shear strain. I think the next, yeah, here it blows it up a little bit. So here we have this gamma 1 and gamma 2. That is the shear strain that we're after. It's the sum of those two. If you want to look at that more, your Mechanics of Materials book, I don't know if that's still the book you use, but any Mechanics of Materials book should cover that for you. So that other type of strange gauge rosette is equiangular. It's this one here. So here we just don't have them aligned to the X and the Y direction. The X direction is still just this gauge, but for Y, we need to use all three. And for the shear, we need to use the 60 and the 120. And then all three of those get used up here to find the strain in any particular direction. Both of these are pretty commonly used. I definitely remember that with this one, quite obviously, it's much easier to get the strain in the Y direction. It's just equal to the strain you can get from the strain gauge output here. There is a slightly different advantage for this one. I'm forgetting right now what that is exactly, but both of them are commonly used. You can use both of them to get what you need in most cases. That is it. See you later.